Dear students, here I am sharing the next part of strength of organic acids and bases. In previous video, we already started the discussion about the aromatic acids. And in that discussion, we have already completed 2 points, that is substitution, alkyl substitution on aromatic ring. The second point that we discuss is introduction of electron withdrawing group. Now, the third one is, no doubt here also we are going to talk about the introduction of electron withdrawing group, but in previous point, that is number 2, there which group we discussed? We discussed the nitro group in that slide. Now here we are going to talk about the introduction of electron withdrawing group, that is hydroxy, methoxy and X, that is halide, into the benzene ring. So the first compound, that is A, benzoic acid. In the second compound, there is a hydroxy group at ortho position, and para position again it's a para hydroxy benzoic acid, ortho hydroxy benzoic acid. Now hydroxy group, so whenever hydroxy group is present in the aromatic carboxylic acid, so look at the pK value. So benzoic acid pK value is 4.20. Ortho-hydroxybenzoic acid pK is 2.98. So this pK indicate what? Smaller the pK value, stronger is the acid. So it indicate what? Ortho-hydroxybenzoic acid is a strong acid as compared to para-hydroxybenzoic acid and benzoic acid. So why this happened? Now hydroxy, methoxy and X, these are electron withdrawing group. So these groups show minus I effect. As the heteroatom is present, so all heteroatoms are electronegative. So because of that, all these groups show electron withdrawing inductive effect. But if when these groups attach to aromatic or conjugated system, then these groups also show electron donating mesomeric effect or resonance effect. So remember, when they are alone or when they are not attached to the conjugated system, then these groups always show minus I effect. But if these groups are attached to conjugated system, so aromatic ring, this is a conjugated system. When these groups are attached to conjugated system, now instead of minus I effect, now which effect they show? They show the electron donating mesomeric effect and electron donating resonance effect. Now why this happens? So whatever the unshared pair of electrons on oxygen are there, that electrons involved in resonance. So as they involved in resonance, so we call it as a electron donating resonance effect. When such groups are present in the ortho and para position, then para substituted acids are weaker acids than meta acids. When such groups are present at ortho and para position, then always para substituted acids are weaker acids than ortho acids and meta acids. The behavior of ortho acid is often different. So let us restart the disconnection. Let us restart the discussion of this. So here that I have written order of acidity is ortho-hydroxybenzoic acid is strong acid as compared to para-hydroxybenzoic acid, and then as compared to benzoic acid. So let us start with the first ortho-hydroxybenzoic acid. So first step is the dissociation of H plus ion. After dissociation of H plus ion, whatever the carboxylate ion is generated, that carboxylate ion forms a hydrogen bonding with this proton which is attached to the oxygen atom. So this type of hydrogen bonding, we call it is within the molecule. So we call this as an intramolecular hydrogen bonding. So this carboxylate ion, that O minus, as this proton having a partial minus sign and this proton having a partial plus sign, and this is a partial minus sign. So because of this partial plus sign, this oxygen and hydrogen forms a hydrogen bonding within a molecule. So it is called as intramolecular hydrogen bonding. So because of this hydrogen bonding, this oxygen with a negative charge, this negative charge means electron density is transferred towards the another atom for the formation of intramolecular hydrogen bonding. So in other words, what we call, there is a delocalization of charge. So this delocalization can be possible by way of a electron withdrawing resonance effect shown by this carbonyl group. So that you can show the electron withdrawing resonance effect like this by doing by the reaction with by the carbonyl group of this. So which effect is present here? That minus R effect is present. But at the same time, which another factor we can find over here? There is a formation of a intramolecular hydrogen bonding. So these are the two effects which are responsible for the stability of conjugate base, and we call it is a highly stable conjugate base. So intramolecular hydrogen bonding stabilize the conjugate base. Conjugate base is highly stable, so rate of dissociation is fast. Hence, this is a strong acid as compared to para-hydroxybenzoic acid and benzoic acid. Now, this is the benzoic acid, and this one is the para-hydroxybenzoic acid. So benzoic acid 4.20 and para-hydroxybenzoic acid is 4.58. That means para-hydroxybenzoic acid is weak acid because the pK value is large. So why this happen? So look at here, after the dissociation of this proton, the conjugate base which result in this case, as we discussed in previous slide, that is there is a presence of intramolecular hydrogen bonding. Such type of intramolecular hydrogen bonding is absent for the stability of conjugate base. So it is unstable conjugate base than the conjugate base of benzoic acid. So why this conjugate base is unstable? The reason for this due to plus M effect of hydroxy group. So what is the plus M effect? So this electron of the oxygen involved in the resonance of aromatic ring, because of that, this aromatic carbon having a negative sign. Because of this negative sign, now the resonance that we can show with this carbonyl group, that this negative charge can be delocalized by way of a minus R effect. So this effect is what? This effect is minus R effect. And then this effect is what? This effect is a plus M effect. Because of that, there is a more electron density on this carbon. As this carbon having more electron density, so we call this is a electron donating group. So this entire ring is what? Instead of it is now electron withdrawing group, now this is entire group is electron donating. So as the electron donating group is there, so because of what? There is a localization of negative charge. As there is a localization of negative charge means what? The stability of conjugate base decreases. Hence, this conjugate base is less stable. Hence, dissociation is slow. Therefore, it is a weak acid as compared to benzoic acid. Now, in case of benzoic acid, which effect is absent? In case of benzoic acid, only this carbonyl group show minus R effect, while this aromatic ring show a electron withdrawing inductive effect, that is minus I effect. As there is no any substituent on the aromatic ring which can donate the electron density, so this ring shows minus I effect. Because of that, minus I effect stabilize the conjugate base. Hence, the conjugate base of benzoic acid is more stable as compared to the conjugate base of para-hydroxybenzoic acid. Now this is the next example here in which the ortho positions of the carboxylic acid group having the hydroxy group. So hydroxy group, actually it is electron withdrawing group, but now it is attached to aromatic ring. Therefore now it shows electron donating mesomeric effect. How it shows the mesomeric effect that we already discussed in previous slide. So this is an example of a 2,6-dihydroxybenzoic acid. So look at the pK value is 1.30. So that indicate it is a strong acid. Now presence of 2OH group at ortho position. So it forms strong intramolecular hydrogen bonding that we already discussed in previous slide how it forms hydrogen bonding. So conjugate base is highly stable as compared to previous example. Therefore, rate of dissociation is fast. Hence, it is strong acid among all. That is ortho 2,6-dihydroxybenzoic acid is strong acid as compared to which one? Ortho-hydroxybenzoic acid. After that, uh, benzoic acid, and after that is para-hydroxybenzoic acid. So the among all the structure, para-hydroxybenzoic acid is weak acid, while 2,6-dihydroxybenzoic acid is a strong acid. Now the next one, dicarboxylic acid. Dicarboxylic acid means presence of two carboxylic groups. This is an example, first of all, formic acid. Now this hydrogen is replaced by one more COH group. So name of this compound is oxalic acid. So two acid functional group is there. So we call it as a dibasic acid. Same, the another example is acetic acid, and one of this hydrogen is replaced by COH group. So this is COH, CH2 and COH. This is the next acid that is again a dibasic acid. Name of this compound is malonic acid. So what we are going to do, we are comparing formic acid with oxalic acid, acetic acid with malonic acid. So you look at here, formic acid pK value is 3.77, oxalic acid pK value is 1.23. So what you see over here, the pK value decreases. pK decreases means what? The oxalic acid is a strong acid as compared to formic acid. Same, it is true over here in acetic acid, it is 4.76, malonic acid, it is 2.83. Indicate what? Introduction of one of the COH group. Again, one more COH group, if you added, the acidity automatically increases. Now, you have a question that is, what is the role of COH group? As the COH group itself has an electron withdrawing inductive effect, that is minus I effect. As I told you, whenever a electronegative atom, or we call it is a heteroatom, is present, then it always show a electron withdrawing effect. And as this COH group, if it is in conjugation, then we had to say that is which effect, that this carbonyl group shows a electron withdrawing resonance effect. Otherwise, overall, it shows minus I effect. The presence of second such group in an acid is expected to make it stronger. Why? Because minus I effect increases due to the addition of one more COH group. Which effect increases? The effect minus I effect increases. So oxalic acid is strong acid as compared to formic acid. The reason, as soon as there is an increase of minus I effect, automatically it stabilizes the conjugate base. As the conjugate base stabilizes, then the rate of dissociation is fast, and hence it is a strong acid. So malonic acid is also strong acid as compared to acetic acid. So dicarboxylic acids are always strong acid as compared to its monobasic acid. That is, if hydrogen is replaced by COH group, then that oxalic acid is strong acid as compared to the formic acid. The reason behind it, the role of COH is showing a electron withdrawing inductive effect. So electron withdrawing inductive effect stabilizes the conjugate base. hence rate of dissociation increases, so acidity also increases. That's why pK value go on decreasing. So this is now the next example. Here, these are the introduction of COH group on aromatic ring. So here only one COH group, that is benzoic acid. Here there are two COH group on benzoic acid and the relation is again a ortho to each other. Here these two acid functional groups are meta to each other. Here these two are para to each other. So look at the pK value 4.17, 2.98, 3.46 and 3.51. So what you see here, when you compare between these two, look at the as A, the pK value is larger. So among all the structure, A is a weak acid, right? So A is a weak acid means there is absence of COH group. Absence of COH group means what? The minus I effect is less in case of carboxylate ion, or we call it is a conjugate base of benzoic acid, that is a benzoate. So here minus I effect is less. Strength of minus I effect is less means what? The conjugate base is less stable. So as the conjugate base is less stable, so the rate of dissociation is slow. Hence it is a weak acid. Look at now here. Ortho is a strong acid as compared to meta, as compared to para. So you can see the order here, that B is strong acid as compared to C, as compared to D. What is the reason behind it? That look at the third point. As minus I effect depends on distance, so distance increases, the minus I effect increases from B to D. So strength of minus I, strength of electron withdrawing inductive effect decreases from B to C to D. The reason behind the inductive effect depends on distance. So as the strength of minus I effect decreases, so stability of the conjugate base decreases in the same order. So conjugate base of B is more stable as compared to C, as compared to D. So as the conjugate base of B is more stable, therefore B is the strong acid as compared to C, as compared to D. So the final order of acidity is B is a strong as compared to C, as compared to D, and A is weak acid among all. The last factor under the heading of strength of acids, strength of organic acids. Now, which is the another factor that responsible for the acidity, and that another factor is temperature and solvent. So what is the effect of temperature and what is the effect of solvent on the acidity? That we have to discuss over here. So what is acid strength? Acid strength is nothing but a pK. Is related to the acidity constant Ka. What is Ka? Ka is the acidity constant, that is the equilibrium constant. So what is pK? It is the negative log to the base 10 of dissociation constant. So dissociation constant is important rather than pK. So equilibrium constant Ka varies with solvent as well as temperature. So how is the relation? Ka. Now, whenever you are going to show a dissociation, always there is a formation of a conjugate base and conjugate acid. Now, as you know, conjugate base there is a negative charge, conjugate acid there is a negative charge. So these two are the ionic structures. For the stability of these ionic structures, you need a solvent. And for the dissociation, again, for the dissociation of acid, generally we need the polar solvent. So if you use the polar solvent, what is the role of polar solvent? Role of polar solvent is to stabilize the conjugate base as well as conjugate acid. So that because of this solvation, then the rate of dissociation increases. As the rate of dissociation increases, therefore automatically the dissociation constant also increases. So if you select the polar solvent, then the pK value also, now there is an inverse relation. As dissociation constant increases, the pK value decreases. It's a inverse relation. So as we are using a polar solvent here, so what is the role of polar solvent? Just now I said that this polar solvent stabilize the conjugate base as well as it stabilize the conjugate acid by the way of a solvation. Because of this, rate of dissociation increases. Rate of dissociation increases means the pK value decreases. pK value decreases means it has to be a strong acid. So solvent plays a major role on the acidity. If we take a non-polar solvent, in non-polar solvent, such type of solvation is not possible. Hence, because of that, non-polar solvent, the acidity also decreases. Now, what happens with the temperature? As you increase the temperature, then dissociation also increases. As the dissociation increases, automatically equilibrium constant also increases. So as equilibrium constant increases, pK value decreases, so acidity also increases. So the major effect of the solvent and the temperature on the pK value or the acidity. So solvent, if you use the polar solvent, it increases the acidity. If you increase the temperature, it also increases the acidity. So with this, I finish now. For this, I always suggest you go through the reference book. So this is the some of the reference book I have mentioned here over here. Thank you.